So this is a lesson 5.3 on the transformations of sinusoidal functions. So last class or last unit 5.2, we learned how to graph the sine and cosine functions, which is short term for sinusoidal functions is short term for both the sine or the cosine curves. Um, so we'll hopefully have practice at drawing those smooth curves. And today we're going to look at some of the transformations that apply to that. So way back early in the year, we discovered transformations of other functions such as quadratics, the reciprocal, the absolute, and recognizing the attributes of A, K, C, and D. Well, we're going to see those all again and how they apply to sinusoidal functions and some of the different terminologies or how it affects the graphs in itself. So the success criteria for this unit or this section is that you'll be able to describe the transformations of sinusoidal functions. So given a graph or given an equation, you'll be able to describe the transformations. And then from that, hopefully we can understand the impact of the transformations on the peak of the graph. So again, peak was the maximum, the trough of the sinusoidal graph or the minimum, the amplitude in the equation of axes, and eventually the period of the sinusoidal function itself. So recognizing how A, K, C, and D affect those various attributes of our sine and cosine graphs. So we'll start off with an example where here is just a vertical transformations, and there were transformations that affect the y value. So let's start off with just our parent function of f of x equals sine of x. And so from our lesson last time on graphing, we talked about the 5-point system of graphing a sine graph or cosine graph. And the x values were the same for both, and those are important points, is that we're looking at 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. And knowing how the sine graph behaves, we hopefully determine that it starts at the equation of axis 0, goes up to the maximum of 1, comes back down to the equation of axis of 0, then it takes our trough of -1, and then comes back to the midpoint again of 0. So let's graph this on our grid here. And for our scale, maybe every 3 I will make 90 degrees. So 90 degrees there, 180, 270, and 360 would be there. Oops, there we go. And in this case, for the y scale, so the y-axis, we'll make every single line to be the value of 1. So let's plot this in red, where 0, 0 is there, 90 degrees and 1 would be there, 180, 0, 270, -1 brings us down there, and 360, 0 brings us back to the midway point. So again, that 5-point system, we have to get very comfortable with that for this unit. So let's connect the dots in a smooth curve. That looks like a sine wave. There we go. That looks pretty good. So how do we graph the transformation? Well, we'll go back to our mapping notation. And in here, we recognize that the A value is 3 and the C value is -2. So in this case, our new y prime is based on our original y. It's going to be 3 times y minus 2. So our x values stay the same. So 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. So how do we calculate new y values as we go through our mapping notation? Here we get 3 times 0 minus 2 is going to be -2. 90 degrees is going to be 3 times 1 minus 2. So that's going to give us a value of 1. And then 180 is really the same as 0. So 3 times 0 minus 2, that brings us back down to -2. And 270 degrees, that's going to be 3 times a -1 minus 2. That gives us -3 minus 2, which is -5. And then 360 degrees, we're back to that equation of axes. So 3 times 0 minus 2 is -2. And if we're to plot this, here we got 0, -2 would be right there. Then we got 90 and 1, which coincidentally, it's just a coincidence, falls in the same point as our parent function. And then 180 and -2 would brings us back down here. Finally, 270 and -5 would bring us over here. And then 360 -2 brings us back to the equation of axes. In other words, to graph the equation of axes, it would be right there. And notice that we have several points that actually fall on that. So here's the graph of the transformation. Again, connecting it with a smooth sinusoidal curve will look something like that. And here, this is g of x. And I should have did the red as f of x. That's my parent function. So looking at the vertical transformations is actually pretty straightforward. The ones that are going to be more tricky is the horizontal. So let's move on to the next example where we do have this. So back as a review, when we look at this, we have to remember to factor out the k value that's inside our function. So again, inside our function is within those brackets. So let's rewrite this equation as sine of, and I have to introduce a square bracket because we have two sets, just to make it clear. We have 3x minus 30. Oh, I should have had a degree sign there. So here, this gives us a k value of 3 and a d value of 30 degrees. So that's going to be important when we actually graph our transform function, but let's quickly do, as practice, the parent function again. So f of x is sine of x. So important points are 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. And it goes from 0, 1, 0, minus 1, 0. Let's draw the scale. So we keep the same scale as before. Let's say every 3 is 90 degrees. Find 360 to get us there. So in this case, because we don't have any vertical transformations, I'm just going to increase our y scale a little bit so that every 2 lines is 1. Just so we get a better view of what's happening with this graph. So let's go off and plot our parent. So 0, 0, 91, 180, 0, 270, -1, and 360, 0, and connect them with a nice smooth curve. So it looks something like that. And that's f of x. So let's get our transformed points. So here, our mapping notation, there's our new x prime is going to be x over k plus d. Well, we know that we just said that k was going to be 3 and d was 30. So given 0, so we need to take 0 divided by 3 plus 30. That's going to give me 30. And then the next one is going to be 90 divided by 3 plus 30. Well, 90 divided by 3 is 30 plus 30 is going to be 60. Next one is 180 divided by 3 plus 30. Well, 180 divided by 3 is 60 plus 30 is going to give us 90 degrees. And then 270 divided by 3 plus 30. That's going to be 90 plus 30, which is going to be 120 degrees. And finally, the last one is 360 divided by 3 plus 30. 360 divided by 3 is 120 plus 30 is 150. So notice that hopefully you recognize that there is a bit of a pattern that's happening within our x values. And this is nothing's happening over y values. We have the same y value. So it's going to be 0, 1, 0, minus 1, and 0. And algebraically, we could actually look at it as well. 30 minus 30 is 0. So what's the sign of 0? It's going to be 0. 60 minus 30 is 30 times 3, which is 90. So what's the sign of 90? Which is 1. And we can do this likewise with the rest of the points. And that could be another way we determine those y values. So let's plot that. So we got 30 and 0. So 30, each line on our x-axis is 30. So there's 30, 0. 61 would bring us up here. And then 90, 0. 120, -1. And finally 150, 0. So again, connecting this with a smooth curve is a little bit tougher because we see that this graph is going to be it's really compressed based off our parent, and that was a pretty decent job. So that's what our g of x looks like there. Okay, so we can see that when the k value is 3, is compressed by a third, and recognize that that's really compressed. But hopefully we can see that also within here, what's their actual period, and we can see that also in here what their x values. Our period is actually 120 degrees. And notice that there's a relationship there between 363 and the actual new period. And we'll explore that in a second. Well, let's explore that right now. So in general, we could be given an equation that looks like this. So really based off our units from before, I think it was chapter 2, that f of, oops, I don't want to highlight. That in general, we have g of x is equal to a times f of k x minus d plus c. Well, all we're saying here is that f of x is the sine of x. That we're transforming the sine function, and all those attributes apply. So in particular, how does it affect the sinusoidal function? So here A affects the peak and trough. So if we're stretching or compressing our graph, obviously our peak or trough is going to come up or down by a factor of absolute value of A. And more importantly, recognize that the amplitude of our sinusoidal function is going to be the absolute value of A. C, we're actually moving the entire graph up and down. So yes, this is going to affect the peak and it's going to affect the trough. But we could also determine in general that this brings our equation of axes. Normally is y is equal to 0, but if we're going to move it up and down by c, then the equation of axes becomes y equals c. As I just highlighted before, we know that k, because we're stretching and compressing, we're actually going to change our period. And the actual relation is that since k affects the period by a factor of 1 over k, and there's stretch and compression by 1 over k, the new period is actually 360 divided by k. So that's how we determine the new period. And I'm just going to make an extra note over here. So here we got period. Oh, highlighter again. I don't want highlighter. We have period is equal to 360 divided by k. Well, if we're given the period, we could actually rearrange this equation, and really the k value is 360 divided by the period as well. Finally, the last thing that we want to look at is the d value. So this is going to shift the graph left or right. So left if its d is negative, right if d is positive. So we're going to say by the absolute value of d units. But when we talk about sinusoidal functions, we want to use the term phase shift. So we're going to say this is going to be a phase shift of so many degrees left or right. So let's go through a couple examples. Oh, not a couple, 4. So let me do this in a different color just to sort of highlight or separate things out a little bit. So as usual, we always want to find the A, K, C, and D values. So in this case, A is 3. This tells me that this is a vertical stretch by a factor of 3. As it applies to sinusoidal functions, this means that we also have an amplitude of 3. So it's kind of convenient. We have A amplitude starts with A. That's a nice, easy way to remember things. The next one we're going to look at here is K. So K happens to be 1, which is uninteresting because there's no stretch or compression, but we still need to identify what the period is. So here the period is going to be 360 degrees divided by 1. Well, it makes sense that the period stays the same as 360 degrees. The d value here is 30 degrees. Notice I'm mentioning degrees, I'm mentioning the unit. That's going to be important for you to do as well. So here d is 30 degrees, and here we're going to have a phase shift of 30 degrees to the right, since d is positive. And finally, we have c is equal to 1. So this implies that the graph is shifted up by 1 unit. So this implies that our new equation of axes is y is equal to 1. Okay. So let me do this other one in red. So this other one is a little bit more tricky because we actually have a k value in here, and worse yet, it's not even factorable for us. So let's rewrite this equation with a k value factored out inside our function. So I introduce a square bracket there, so it's going to be 4, and 180 divided by 4 is 45 degrees minus 5. And we go through the same process. A value here is -2. So here we have a few things. We have a vertical stretch by a factor of 2. This is also reflected in the x-axis. Or vertically reflected, I'll accept both. More important is as it pertains to a sinusoidal function, this makes the amplitude is equal to 2. The next thing we'll look at is k. K in this case is 4. So this applies a horizontal compression because it's going to be 1 over k, so it's less than 1. And so here the factor by a factor of 1 over 4, so 1 over k. And as it pertains to sinusoidal functions, we need to figure out what the period is. So the period is going to be 360 degrees divided by 4, which is in this case 90 degrees. Find the last attribute, 2. D is in this case 45 degrees. So we have a phase shift of 45 degrees to the right, since D is positive. And finally, C in this case is a -5, so that implies that it's shifted down by 5 units. And that implies our new equation of axes is going to be y is equal to -5. Okay, let's look at the next example. It's close, but really the same thing. So we're just transforming sine. F of x in this case is going to be cos of x, but we go through the same process. I'll do this one in green. So here my a value is 3/4. So what does that imply? That here in this case we actually have a vertical compression of 3/4. As it pertains to a sinusoidal function, that means our amplitude is actually 3/4 as well. Like the first example, k here is 1. So not interesting in some sense, but we still need to identify the period. The period is 360 degrees. D, in this case, is -90 degrees, so let's not get mixed that up. Again, my trick remembering this is looking inside my function. What value of x makes that 0? So this is going to be -90. So here we're going to have a phase shift of 90 degrees, in this case to the left. And the last thing here, we have c is equal to -12. So this is shifted down by 12 units. So this implies our new equation of axes is y is equal to -12. In other words, the halfway point of my graph, that's why the equation of axes is important. In a sinusoidal function, it tells us sort of like the halfway point of our graph. And the last one, let's recycle back to blue. And like the second example, there's a pattern there, we need to factor out the k. So here we got y is equal to 4 times the sine of 2. And 120 divided by 2 is going to be 60 degrees plus 3. So my a value is 4. This implies a vertical stretch by a factor of 4, which in case in the sinusoidal function means that the amplitude is 4. Here we have a k value of 2. So here we have a horizontal compression by a factor of 1/2, or 1/2. And this implies that we have a period. It's going to be 360 degrees divided by 2, which is 180 degrees. So we can see that it's going to be compressed. And here our D value is 60 degrees. So it implies a phase shift of 60 degrees to the right. And finally, we have a C value of 3, which means that the graph is shifted up by 3 units. And more importantly, for the sinusoidal function, that means the equation of axes is going to be y is equal to 3. Okay, so given an equation, that's how we sort of pick out the transformations, and more importantly, how we could go off and define the amplitude and the period and the phase shifts, and the new equation of axes of our sinusoidal function. Now we're going to look at, given a graph, how can we determine an equation? And I just want to highlight that notice that in here it says a possible equation for, in this case, we're looking for a sine function. So when we say possible, that means that yes, there might be different answers that all are correct. And so that what we're going to recognize is that because the sinusoidal function, whether sine or cosine, because it's repeating, if we shift that graph left or right a certain amount, we're going to get the exact same graph. So maybe I'll show that in class when we have a chance, maybe in something like what's that? Not GeoGebra or Desmos. I could show you maybe how that works. This is actually kind of interesting. And so why things kind of seem easy, or hopefully maybe seems easy up to now, things can get kind of confusing because of the multiple answers that we might get for a given graph. But I still like to go through a particular process and always identify the peak trough. So in this graph, we can see that the peak is 3. The trough is -3 as well. Sorry, not as well, but -3. So equation of axes. So this is actually pretty straightforward, but I'll just write down the equation again. That's going to be the peak plus trough over 2. In this case, it's going to be 3 plus or minus 3 over 2, which is 0. The amplitude is going to be peak plus trough over 2. Sorry, not peak plus trough, peak minus trough. Make sure you don't confuse those two. So peak minus trough, in this case, 3 minus 3 plus a minus 3. So 3 minus a negative 3 over 2, which is going to be 6 over 2, which is 3. Okay. It's actually easier to see from the graph. If this was the equation of axes right here, we know it's y is equal to 0. The amplitude here is actually 3. And the amplitude down here is also 3. The period, so we have to go back and look at the graph. So one technique or one strategy we take is looking at the peak, but unfortunately I'm only given one peak over here. I could also look at the trough. That could be the trough there. It's hard to determine. And worse yet, the troughs are not at a crosshair, so it may be a little bit hard for me to determine the exact value. So the other strategy I'm going to take here is looking at the x-axis, where it's crossing the x-axis, so it's crossing it there, which is wonderful. It happens to be at 0. And then notice that it's not here. That's not where the end of the cycle is, because in this point, the graph is going up, but given this point, the graph is going down. So that's not where the cycle ends. The cycle end is actually going to be over here, where the graph is going back up again. So that's where the repetition is. And it's hard for me to see the numbers. Oh, there we go. So that's 90. So this is 180 degrees. And this is 0. So here we see that the period is 180 degrees. Okay, so let's go back and do that. So the period here is 180 degrees. And for the phase shift, well, do this in blue. Sine starts right there. So in this case, we actually have no phase shift. So the reason why it's nice to pick off these attributes is we could get our A, K, C, and D values straight from here. So I'm going to do this in red. So we're going to do the sine function. So equation of axes is y equals 0. This implies that C is going to be 0. The amplitude is 3. That implies that A is going to be 3. Well, period is 180. So we know that K is 360 degrees divided by the period. In this case, is 180. So we know our K value is going to be 2. And here we don't have a phase shift. So that implies that D is going to be 0. So C and D are both 0. So that makes our equation a little bit simpler to do. So my A value here is 2 times the sine. My K value is 2 as well. So maybe not the best example to sort of highlight the differences. We don't have a phase shift, so we end that equation, and we don't have shifted up and down, so we're not going to add 0. So that's our final equation right there. For this other graph, we're going to do the same thing. So let's get the peak. So peak is going to be 2. The trough in this case is 0. So equation of axes again is going to be the average of the two, which is going to be peak plus trough over 2, which is 2 plus 0 over 2, which happens to be 1. And let's kind of draw that, kind of see things, and maybe that will help me get my amplitude correct. So here the amplitude is going to be the peak minus the trough over 2. So here's going to be 2 minus 0 over 2, which happens to be the same thing coincidentally. So which is going to be 2 over 2, which is 1. And I can kind of see that in the graph, that the amplitude is 1. The period. So on this graph, it's really tough to pick off the period. Several reasons why. Well, I can look at the peak. I can't find the other peak. I can look at the trough. I can't find the other trough. At some point, we can see sort of might be repeating somewhere over here, but it might be hard to detect exactly where. If I sort of continue this graph, so then my other thing of where, in this case, identify where the equation of axes is, where the graph is passing that, we can see it there, and maybe we can estimate that that's minus 30 degrees. Okay, and in fact it is. But you might be wondering, well, how can we actually guess that? So I'm going to show you another strategy that is a bit more foolproof. In this case, because we're not given a clear cycle in our graph, it's there, but it's hard to pick off, I'm going to identify the peak and the trough. So here's the peak, and there's the trough. It's kind of clear. Unfortunately, it's not a crosshairs, but I can see that the peak is between 0 and 30. So maybe that's 15 degrees. And I can see that the trough is between 90 and 120. So halfway between there, 105 degrees, let's say. Okay. One thing we're going to recognize with sinusoidal functions is because it's periodic, it's the same distance between the two, is that when we have the distance from peak to the trough, that's always going to be half of our period. Okay, so I'll say that again. The distance from the peak to a trough is always going to be the half of our period. So in this case, the distance from 15 to 105 is actually 90 degrees. But like I said, that's half of my period, so I need to multiply by 2, and so my period is actually 180 degrees. So we'll fill that in. Period is 180 degrees. Okay. The next part is also tricky in trying to determine the phase shift of this, because it doesn't start off at the same place, right? For the sine graph, if it's to start off at the same place, we know that the midway point would start at 0, but it doesn't. So what we need to do is we need to find our equation of axes and find where in that graph is the sine curve going up. So here is a point on our sine graph where it's at the equation of axes, but here it's going down. So that's not where the sine graph starts. The sine graph starts the equation of axes and goes up. So we keep coming along. Oh, we find that point. And at this point, the graph is going up. So we can say that that's where the sine curve starts. So in this case, that's at 150 degrees. So we can say that this phase shift is 150 degrees to the right. Now, this is where we get many possible answers, because basically we extended our graph and we look to the left over here. Oh, the sine graph could actually be viewed as starting at negative 30 degrees. So another possible phase shift is actually minus 30 degrees. So in this case, we could actually come up with two equations for this. We could come up with y is equal to, well, my amplitude was 1, so we're not going to write the 1. Sine, my k value here, oh, I didn't calculate the k value. So this implies that the k value is 360 degrees over 180 degrees, which happens to be the same as our example, which is 2. So I'm going to do square brackets because I know there's going to be a phase shift. So this could be the same thing as 2 if we use 150 to the right as the phase shift. And this graph is shifted up 1, so that is one equation. And another equation, it could be sine of 2 times, in this case we have a phase shift 30 degrees to the left. That's going to be x plus 30 degrees plus 1. Okay, so this is where the unit sort of takes on to be pretty tricky, in that we can have multiple answers to our graph. To make things more confusing now, we're going to see that the sine and cosine graphs are actually the same. So here's two examples where we could actually interpret either one of them, the graph to be either a sine or cosine. So let's step through the process. Again, always, to me, the easiest way to do this is to always identify the peak, because we could see that. Oh, well, maybe not. I'm going to say that this graph, the numbers of this graph are kind of hard to read. First one's okay, second one is tough. So let's put in some numbers here. It's even hard for me to read. I believe that's a 3. So that makes down here negative 1. And I believe that the intervals that they're going up by here are 90 degrees. So this is actually 90 degrees. This is 180. This is 270. This is 360. This is 450. And 540. And 630. Etc. etc. So each line is 90 degrees. So that one's not clear on that graph. So let's go off and do this. So what's the peak of the first one? Well, the peak is 1. What's the trough? Is minus 3. And why I like picking off the peak and the trough is based off of that. In other words, what's the max and min? We could get two of our attributes. The first one is the amplitude. So amplitude is peak minus trough over 2. So in this case, it's going to be 1 minus a minus 3 over 2, which is 4 over 2, which is 2. Once we have the amplitude, that means we have the a value is 2. Next one we're going to do is the equation of axes. And we said that it's going to be y is equal to peak plus the trough over 2. So in this case, it's going to be 1 plus a minus 3 over 2, which is equal to minus 2 over 2, which is minus 1. In our equation, then it's maps to our c value. So immediately just peak and trough. We got our a value and our c value. Next one is a little bit more tricky, but not terribly difficult. Is just go off and identify the period. So here we're going to look at a graph. I might look at maybe this point here. So maybe I'll go from peak to peak. And I'm going to see that that's minus 30 degrees. And over here, that's 90 degrees. So how do I go from negative 30 to 90? That's going to be 120 degrees. So my period is 120 degrees. So that implies that my k is going to be 360 degrees divided by 120 degrees, which is 3. So the next part is, again, tricky in terms of identifying the sine. So again, I'm going to draw my equation of axes, which is negative 1. And again, I want to go along my equation of axes and see the points where it hits the graph. And again, the sine curve starts going up. So that rules out that point. It starts going up from there. So that's one possibility. Not there because it's going down. But that would be another possibility. It's going up, not there because it's going down. And finally, that might be another possibility. It's going up. So I'm going to make things easy. I'm just going to choose this point over here, and that's at 60 degrees. So here the phase shift. This is 60 degrees to the right. But I'm going to write in here, this is only for sine. Okay, so what's our equation for sine? So that's going to be y is equal to, well, my a value is 2 times the sine. My k value is 3. And I know we're going to have a phase shift, so it's going to be minus 60 degrees. And then minus 1. That's my c value. So at the very beginning, when we talked about 5.2, when we talked about the similarities of sine and cosine, is that we know they have the same amplitude, we know they have the same equation of axes, and we know they have the same period. So that's the nice thing about this is, because we got the amplitude, equation of axis, period, we already got 3 of the 4 attributes that we need for the cosine function. The other thing we need to do is find the phase shift. Well, actually, it's a lot easier to do with sine to find the phase shift, because what we're looking for is a maximum. So there might be 3 possibilities, but again, I'll keep things simple. I'll use that as the maximum, and that has a phase shift of 90 degrees to the right. So therefore, this could be 90 degrees to the right, and that's for cosine. So my equation for cosine is y is equal to 2 times the cos of 3x minus, in this case, 90 degrees, minus 1. So notice that 3 of the attributes are exactly the same for sine and cosine. The only difference is going to be the phase shift. Okay, so let's look at the next example. Let's give that a go. So again, easiest thing for me to do is quickly identify the peak and the trough. What's the highest point? Well, that's 3. And what's the lowest value is minus 1. So from there, I could get the amplitude. So this is going to be 3 minus 1 over 2. In other words, 3 plus a negative 1 over 2. And that's going to be 2 over, no, sorry, 3 plus 1. Let me try that again. The amplitude is peak minus the trough over 2, which is 3 minus a negative 1 over 2, which is 4 over 2, which is 2. It's a lot easier to see in the graph. You can see that it's going to get 1, and you can tell the amplitude. This graph was not 1, but it's 2. The equation of axes, that's equal to y peak plus trough over 2. So in this case, that's 2 over 2, which is 1. So I was actually doing the equation of axes by accident before, so we need to be careful. So from here, we could determine that for the original one, first one, amplitude, that means a is equal to not 1, but 2. And here, the equation of axes, that's equal to 1. And I'm going to quickly sketch that. So there's my equation of axes. Looks like the midway point. I can confirm that the amplitude is 2 by either going from the peak or the trough. That is 2. And the next thing we want to do is just go off and get the period. So, this one might be easier because there's a trough there. It happens to be at 0. There's a trough right there, and it happens to be at 360. So here the period happens to be 360 degrees. So that implies that my k value is actually 1 in this case. And the phase shift. So I'm going to do this in a different color because I know I'm going to have a different phase shift depending on if I'm looking at a sine or cosine. So phase shift, again, for sine, I'm going to go across the equation of axes and find a point where it starts going up. And there's one right there, and I'll use it. And that's at 90 degrees. So I know that the phase shift is going to be 90 degrees, in this case, to the right. So therefore, my equation for sine would be y is equal to, my a value is 2, times the sine. Since my k is 1, I'm just going to have one set of brackets. And my phase shift is going to be x minus 90 degrees since it's to the right. And this graph is shifted up by 1. Then we'll look at cosine. Again, the only thing we're here looking for is the peak. So there's a peak right there. How much is it shifted by? In this case, that's 180 degrees. So here I could say 180 degrees to the right. And maybe in brackets, I'll say that's for cos. Let me go back in here and say that this is for sine. And so what's my equation for cosine? Well, once we got sine, we're 3/4 of the way there, because the only thing that's changing is going to be the phase shift. In this case, it's 180 degrees plus 1. So that's how we determine the equation from the graph. Is really starting off with the peak and trough, then determine the period, and then probably the most difficult part is identifying what the phase shift is. So go off and do your homework. Hopefully it gives you lots of practice for doing that, and hopefully this video was helpful. That the amplitude, whoa,